In Lesson 1, we were talking very roughly how an atomic force microscope works. Now we're going to go into some more detail. We still have the cantilever. We still have a laser beam bouncing off the reflective backside of a cantilever, and that reflected light goes to a quadrant photodiode. All of this stuff in some AFMs are connected to a scanner, and that moves all these components back and forth in the micron range. Okay? You can also have a scanner on the sample side, and there are advantages and disadvantages to that. So there's the sample. In the particular AFMs I use in my courses, that sample is on a stage. That is a stage driven by motor, and the stage can move the samples in the centimeter range, so you can go across a very large sample and get to near where you want to be. So in the following we're going to refer to directions, and the XY plane in most AFMs is defined to be in the plane of the sample. I use a coordinate system that looks like this, with the positive y direction along the long axis of the cantilever, and the z direction pointing up. So, as I was telling you in Lesson 1, the photodiode sends a signal out, and that signal goes to a computer, and the computer, in what we've done so far, plots essentially the deflection of the cantilever as a function of the XY position. So the computer needs to initiate this process by telling an electronics box to send out a signal to the scanning device to move an X and Y, and also to collect the information of the deflection of the cantilever. So this image you can think of as being the deflection as a function of XY position of the scanner. So this way of operating an atomic force microscope is called the constant height mode. And that's not referring to the height of the sample, it's referring to the height of the scanner. So the scanner doesn't change, or it's unmoved in Z. But the deflection of the cantilever, its bending, that is what's changing. But there's a problem with constant height mode. Let's say you had a cantilever or a sample that was sloped, and you put your cantilever in contact with that surface. When the scanner brings it over to this part of the surface, because the scanner has not changed in height, that is going to be bent way backwards. Well, what does that mean? Well, it means that the force between the tip and the sample here is going to be much, much different than the force over here. And so this over here on the left, that might be causing damage, and it will be hard to interpret an image like this, because over here you would have a large contact area between the tip and the sample, and here a smaller contact area, so you would expect different image resolution. So it's just better in most cases to look for a situation where you can keep the force constant instead of the height of the scanner. So how do you do that? Well, I'm going to do a quick sketch on the next slide and be back to you in a moment after I get that ready for you. Okay, so I have resketched the main components of an AFM, but I have added those things in white, the feedback circuit and the Z electronics mechanism. So what does the feedback circuit do? It tells the electronics, and thus the scanner, that while the scanner is moving back and forth in X and Y, it's also moving up and down in Z. If you remember, Z is the positive vertical direction, such that the deflection of the cantilever stays the same. The deflection of the cantilever is proportional to the force, and it's also proportional to the voltage on the photodiode. So this way of operating, which is the most common way, is called constant force mode. And I bet you've anticipated me. What it means is that the scanner Z changes, whereas the deflection D remains the same, meaning that the force is the same because of the linearity of force and deflection. So if we're going to label our picture on a computer, we would label it Z as a function of X and Y. So in this lesson, I have tried to give you an idea, a firmer idea of how an AFM works, and I hope that you would be able now to go and sketch the components of an AFM. And I've also tried to give you an idea of the two basic operating modes of AFM, one being constant height and the other being constant force. And as a quick summary of those two modes, remember, constant height gives you deflection as a function of XY position of the scanner, whereas constant force gives you a constant force, but the scanner has to move up and down in Z as it goes back and forth in X and Y. So why would you use one mode or the other? Well, constant height mode, because it doesn't have a feedback circuit, which takes a little time to operate, it is faster, but the interpretation of the images is difficult because that force between the tip and the sample changes. And no surprise, the constant force mode, that's got the opposite set of advantages and disadvantages. Well, it's slower, but the interpretation of the images is easier because all points in the image nominally have the same force acting between the tip and the sample, because that's what the feedback circuit does. So later, I think perhaps in two lessons, we'll spend more time talking about the feedback circuit and how you can adjust it to make it work as well as possible. But first, in the next lesson, we'll talk about AFM as compared to other instruments that might be used in nanoscience and nanotechnology.